It's a great pleasure to have Prahar here. And it's going to tell us about an partial derivation of the soft.
Okay, thank you all. It's great to be back at TIFR. Okay, so I'll tell you about a paper that I wrote, this paper that came out earlier this year, in which we presented a derivation of this soft effective action, which was previously kind of written down by guesswork, kind of educated guesswork using some effective field theory methods. We wrote down this action in this paper in 2021. This is work with Dan Capitz. And then in this paper, we kind of derived the action. And I'll explain how we derived it. And of course, I'll explain what the soft effective action actually is, since many of you were not here when I gave my talk at the alpha last time, which was on this paper. I'm also just listing a bunch of papers because this derivation actually requires us to go through a bunch of papers and extract results from like a whole web of different papers. And these two are essentially the main papers where we had to look through various formulas and extract them. So I'll refer to them whenever that comes. And just to make it self-contained, I'll try my best to at least sketch all the formulas that I'm going to end up using. I won't just write down a formula and just say, look at this paper where it's derived. I'll try my best to go through it. And then there was a follow-up paper to this, which is that came out after this original paper, where we actually found that this soft effective action seems to play a very interesting role in many different contexts. So you can, this soft effective action can tell us about entanglement entropy, like the entanglement edge modes in gauge theories. It has to do with Wilson line dressings, like the Fuzzy-Foolish dressings. It has to do with the large gauge charge. And so there's many other kind of features that it seems to be related to. And that was in this paper, and I'll also discuss a little bit. Okay. So, so I'll be honest, unfortunately, I didn't get a lot of time to kind of prepare the talk. So I just printed out the paper, and my goal is just to kind of go through parts of this paper and then see where we get. Hopefully this is the IFR. So for me, I actually consider this to be an internal seminar. Okay. Yeah, no, it's fine. Okay. Yes, I'll tell you what the action is right now. Okay, so let me start by kind of giving a very brief review of this, which will tell you what the soft effective action exactly is. So in general D plus 2 dimensions, so the setting that of my entire talk is going to be D plus 2 dimensional Minkowski spacetime. And I'm going to study an abelian gauge theory in this system. Okay, so here I'm just going to take a U1. Gauge theory. So here's a property of all abelian gauge theories. So if I just take a generic S matrix, so I'm going to denote an S matrix in this way. So I'm going to have some set of hard particles. So here let's think about, I'm just drawing this. So I have some number of particles coming out. They have some charges Q1, QM. And I'm considering such a scattering amplitude. And in addition to these M particles, I'm also including some set of external soft photons. And I'm just going to denote them for the moment with phi. And so I have some set of soft photons here. So here by soft, I mean, so here I have momentum P1 to Pn. And then I have additionally some external set of soft photons, which is Q1, Q2, Qn, this is n, with the statement that Qi is always much less than Pj for any Pj. So let's say the energy. So the energies are much smaller than everything, all other energies in this system. So that's the scattering amplitude. And as you may well know, scattering amplitudes are IR divergent, at least in 4 dimensions. So to actually define the scattering amplitudes, we have to introduce a cutoff. And so I'm going to denote mu as that cutoff. So this makes sense. This entire formula at least hopefully makes sense now. So I'm computing this sort of scattering amplitude. I have M hard particles with momentum P. I have Q soft particles, and because I'm doing gauge theory, the soft particles in question are soft photons. And I'm going to assume that the energy of the photons is extremely small compared to the energy of the other particles. And in addition to all of this, the amplitude is evaluated with a certain cutoff.
So mu sits in the middle between Q and P.
No. So mu is very, very small. And so let me define lambda as, actually it's best to just do it now. So I'm going to define lambda as the cutoff that defines, and this lambda is much, much smaller than any of the previous now. So there's some, so this is not a UV cutoff, just to be clear. This is the cutoff that simply delineates between what you call soft and what you call hard. Then I have some momenta which have energy less than this lambda. And then I just have, I don't allow Q to go all the way down to 0 because the amplitudes are not well defined. So I introduce that cutoff. So this is what mu and lambda.
So Prahar, do you have massive particles in your theory?
You can, yeah, so all these B's can be massive.
And how does it compare to mass, all these scales?
Oh, because this is the energy, right? So the energy, yeah, so maybe,
Okay, fine.
yeah, MI. So, or if they're massless, if they happen to be massless, then it's the energy.
Yeah.
Yeah.
So I should know this, but is the dependence on little mu basically logarithmic?
Yes, in 4 dimensions, it's not.
So, yeah.
I'm just going to write it down.
Okay.
Okay, so this is this is just a generic scattering amplitude.
So mu was the IR cutoff and lambda is.
Mu is an IR cutoff. Lambda is just a cutoff that it's an ad hoc cutoff that I've introduced to differentiate between what I'm calling soft and what I'm calling hard. Just like this.
Yeah.
Of course, the full amplitude does not depend on lambda, but it's as an intermediate scale I've introduced. Okay, and this is a standard QFT fact, which I'm just going to write down for you, that every time you insert a soft photon, the amplitude factorizes into a soft factor and a lower point amplitude. And I'll tell you what the soft factor is, but the general formula actually won't be necessary. The point is that there's some soft factor which I'm going to call J1. So there is a soft factor for phi 1, there's a similar soft factor for all these soft particles. Okay? And so what you get is that the amplitude factorizes into a bunch of these soft factors, and then this lower point amplitude with the same cutoff mean. But this lower point amplitude is IR divergent, and this amplitude additionally factorizes, and you get some factorization of the form e to the minus gamma, this line, okay, and then the lower point amplitude, but now with the cutoff lambda. So the point here is that in going from here to here, I've integrated out all photons that have the energy between mu and lambda. And this factorization, just to remind everyone, is coming from diagrams of this type. So when you kind of integrate out photons that are exchanged between external particles. So here you just integrate out all the photons which have energies between mu and lambda. And the statement is that the contribution of such diagrams, loop diagrams, introduces another factorization. And now I can write down this lower point amplitude at some lambda, and of course my gamma here depends on mu and lambda. I'll write down the explicit formula.
So these virtual photons are between soft photons, or they can be between soft and hard?
No, they have energies between mu and lambda, so they're all soft. So I'm integrating out the soft degrees of freedom.
No, he was asking the solid lines.
Oh, the solid lines are always energetic. So in my case, all the solid lines have momentum pi. So here, all of them. So all of them are hard. So every single one of these is this is sort of the k prime. And then there's some exchange.
So Prahar, if I want to put words to this, one effect that exchange would have is to account for the forces between particles as they move.
Exactly, because the QED has long range forces.
Right.
So
Is there any other effect of that? Is it basically, should I basically think of this as
basically
moving
yeah,
the forces of
it's
outside?
basically that.
And just along those lines, I mean, is this something you would expect just from Wilsonian effective field theory? You have, but please correct me, because I mean, you have these very heavy particles, let's say, in compared to scales,
Yes.
right? And they get produced, or they come in initially, and you can think of an effective field theory, you would think much below their mass.
Yes.
And the input into that effective field theory is something. some very hard stuff, but then you have some answer effect.
Yes, exactly.
And so this is the soft
This is that,
answer.
yeah, this is that, what do you get from that effective, and in fact, that is that soft effective action, that's the point.
But I guess isn't surprising that the effects of all these soft photons is just like an indication of another kind of gamma world. That is surprising.
No, it's, for QED, it's not, yeah, it's not, you can really just, all of this is just, the fact, well, I suppose it's not trivial to show that this loop effect, because of course, this amplitude, when I compute this loop amplitude, let's say I have some off shell, so there's an off shell momentum going through here. I have PK plus L, PK minus L, and here, because I'm not assuming that this is QED, so this is some effective 1pi vertex. So it could well be that this internal line is a different particle than this external line. And so, again, if you think a little hard about it, it's kind of trivial. But the claim is that as L goes to 0, you get a divergent contribution. And in that limit, the only contribution you get is when this particle is the same as that particle, which means this internal scattering amplitude is the same as the original scattering amplitude. Now defined with a different cutoff.
And sorry, Prahar, I mean, in the 90s, Mark Wise and his Mitra student, they developed heavy quark effective field theory.
Yes.
And it was a very similar picture, but even more needed because the strong interaction becomes stronger.
Yeah.
And they did sort of develop this effective field theory in a very similar way. Because
Yeah.
the heavy quarks just go barreling. So it seems, is there even a connect just in terms of how one effectively construct? Of course, here you have QED in the end, probably much more, you can calculate much more.
Yeah, you can calculate everything.
Yeah, and there you can't, but that's the power of effective field theory. You have some universal soft stuff with that. It seems very similar.
Yeah, we have a lot about that.
So, but one question about along the lines of Sandeep's question, you have to know what, if I was thinking in space, you will have to know what trajectories to send these particles on.
Yes.
And that itself is modified by this soft stuff. Right?
Oh, yeah. Absolutely. Absolutely.
So you would need to do that self-consistent.
Yes.
Okay.
Indeed, this is what Ashok, and when he works out these log soft theorems and all, that's kind of what they do. To kind of find every time you exchange a very low energy photon, and because you exchange it infinitely many times, you keep modifying the final momentum by a little.
If you want to keep those guys on shell, maybe Sandeep had a night keeping them off shell, and then
Yes. Yes. So right now, actually, I'm going to eventually show you, in fact, the action that I'm going to talk about, this whole thing.
Actually on shell.
Everything is going to be on shell.
That's what
But I think they were quite moving straight.
Yeah. There is an off-shell contribution.
Because of the 1/r potential, their motion itself is modified, and that will come self-consistently from this exchange. So you have to do some self-consistence.
So here I drew one diagram, but there's actually a sum of diagrams. So maybe
I was really thinking like this, that the hard theory inputs the trajectories, which are input into the soft theory, and then the soft theory for given trajectories finds this dressing, and then you solve for the trajectories in the end.
self-consistent.
Right? I mean, something like that,
Yeah.
right?
Yeah.
Okay, I don't have very precise.
Yeah, that's roughly right.
But your point is.
Just to point out, it's essentially like this. In fact, you're supposed to sum over infinitely many exchanges. And every different exchange kind of changes the momentum by a small amount. What is non-trivial in that in QED, this infinite sum exponentiates into e to the minus gamma, where the gamma is just given by this first diagram.
And is this basically the taking the classical level? Is that exponentiation the same thing?
There is there is a loop correction here also. There's an off-shell contribution to gamma as well. Actually, but we will not be talking about it. It is there. We still don't know exactly how to understand it. For today, I'll just be talking about the on-shell. Everything will be.
But for the trajectory, for the motion of the particle, is that basically?
Yeah, this is basically classical.
Classical motion in the one.
Yeah.
Right? You would expect from a theory of trivial as QED.
Yes.
That's it.
Yes.
That you take one particle moving on. What you have to do is, I would imagine, solve for the motion of that particle in the classical electric field or and that's non-trivial because 1/r.
Yes.
1/r doesn't quite die off too. There's a long prediction, right?
Absolutely.
This usually the reverse summing of the ladder diagram. I mean, the summing of the entire ladder.
Yeah.
That gives you
All of these diagrams you can kind of sum.
Exactly. I felt that the exponentiation was basically making it clear.
Yes, exactly. Absolutely. This is not, so this exponentiation doesn't happen in QCD. Or non-abelian. I mean, QCD there's other problems with confinement, but let's say non-confining.
But I seem to remember this happens to gravity.
It also happens in gravity.
Yeah.
And that's because gravity is non-abelian, but the charge for gravity is energy. And so low energy gravitons don't couple to anything because they're soft. So there's no self-interaction of soft gravitons.
And can you one more, I'm sorry to interrupt, so can you one more time say what part was not classical?
I'm going to write down the formula. Then then I'm going to just drop one term. The rest of my talk, and that's the one that's not classical. Okay.
So they are studying scattering of hard particles, right? Because the IR divergence come from.
The point is that all of these soft terms you can just completely factorize out because of the soft theorems. And then, so these factors J1 to Jn correspond to external soft photons. These guys are on shell. And this e to the minus gamma comes from internal soft photons. So all in all, this full factor captures basically the whole soft contribution to the action, both internal and both external soft photons on shell, as well as the internal ones which kind of run in loops. And then what's left, of course, which is now theory dependent, is the actual hard amplitude, which is some complicated quantity, for which you actually need to compute. And it's theory dependent. The point is that this factor here is going to be completely universal and independent of which theory I'm working, which actual gauge theory I'm working.
Okay, so
Prahar,
that equals to 0, you're saying there's something universal about.
Absolutely. These are all I'll write down formulas. The formulas I'm going to write down for these are just exact formulas in any gauge theory in any dimension, no matter what the action.
And in fact, the hard scattering may not even be due to QED.
Yeah, it may not be the hard.
Some whatever.
Yeah, there could be. I just mean you want gauge theory, but you could have crazy massive scalar fields, do whatever you want.
Exactly. I mean, yours is an effective theory for
Yeah.
so Prahar, one question.
Yeah.
So you mentioned that for, here these gamma is given rise to by the ladder diagrams, which exponentiate and give this gamma, this action, which can
Yes.
And in the theory of gravity also, you said, you made a comment about how these diagrams are also still ladder diagrams because low energy gravitons don't self-couple. But
Yes.
I thought you would have to get out of this the action, Einstein action, right, which has non-linearities. So you would have not just ladder diagrams, but I would imagine couplings of gravitons, with some higher point vertices coupling to external legs, connecting to external legs. And so
In
on.
gravity, you will also have these sort of diagrams.
Yeah.
Right? But they would not be logarithmically divergent. That's the point. The
Uh-huh.
logarithmically divergent diagrams are these simple ones where you just have exchanges with no interaction. Because essentially this interaction piece carries an extra factor of the energy that's running in this loop, and that's already small because I'm looking at the divergent contributions. So and then I have an extra factor of E in the numerator coming just from, well, in this case, it's a 4-point vertex, so E squared. So I'm going to get an extra factor of E squared in this vertex. And so this diagram, when you compute it, will actually not have any IR divergences whatsoever. The divergent part here in this, everything I'm going to talk about this gamma is that the divergent part, the logarithmically divergent part, will simply come from diagrams of this. That is now no longer true in QCD, because now in QCD you have this diagram, but the coefficient, the vertex is not E, is G squared, is GML squared, which is not small at all. So these diagrams will also be of the same order of being logarithmically divergent as these diagrams.
And there's something special happen when the two particles are going in the same direction.
We're not going to address that problem. In QED, that is a problem. So you have additional collinear divergences when two particles sit on top of each other. In gravity, this doesn't happen. This is another miracle of gravity, that gravity has no collinear divergences.
How do you say that this gamma is on ship?
I'll tell you. Let me write it down now since we have had enough questions. Okay, so this soft effective action, so the point of this soft effective action here is the following. So there's an action which there's some set of fields, let me just call them some set of soft fields, which I'm doing a path integral over. Then I write down this effective action of these soft modes. So that's what this soft effective action is. Okay, and for each particle, phi1 to phi n, I insert this in my as operators in my path integral. So because these are soft, by definition, these are the soft photons. So I can't integrate them out. Okay. And then there's going to be another soft contribution coming from these O's. And so for each O, I have a soft insertion U, which I'm just referring to as U1, which is some function of these soft fields.
The coupling to it.
Yeah, it's kind of the coupling of the soft field to the hard field. Okay,
It's not, sorry, please, it's not like a Wilson line.
it is exactly Wilson.
Right.
So this is kind of the low energy effective action. These are the external soft photons that I'm inserting. These are the Wilson line dressings, thank you. And then you compute this path integral and it reproduces this whole factor. That's the point. So that's it. This is what I want to point out. So this is the soft effective action that we wrote down here. The perhaps slightly non-trivial thing that you may not immediately see here, we started in D+2 dimensions. This is all in D+2 dimensions. This soft effective action is a D dimension. It's not a D+2 dimension action.
Because how big K is has gone away.
Yeah. So
Direction.
one is that it's on shell, and the other is that you've taken the soft limit. So you've kind of removed 2 degrees of
The soft limit would be two, this is not clear to me that.
So
2 dimensions less.
roughly it's an L, generic off-shell L has D+2 components. Then I restrict you to on-shell momenta, so L squared is 0, that reduces 1. And then I take the soft limit, that reduces another 1. So only the direction is left. So only the theta phi directions are left on the sphere.
See, but you might have thought that you have to keep all photons which are softer than some kind of,
Yes.
including
So
their magnitude.
Yes.
I mean, that's what Wilson would have
Good.
suggested. And this is like more interesting for me.
Yeah. So I'll write down what this effective action is. I'm just trying to give you a general picture. In this paper, in the one that came out in 2021, we guessed what this action was using large gauge symmetry. So if you have been following, there's been this development of asymptotic symmetries in flat space-time, and we have understood that in gauge theories, you have this large gauge symmetry, which is spontaneously broken in the vacuum. And it's this gauge symmetry that acts on the sphere, on the celestial sphere, so on SD, on a D-dimensional sphere. And it's spontaneously broken. So you can use standard effective field theory techniques to write down the effective action for the Goldstone modes at low energies. And that's naturally going to be a D-dimensional action because it's a D-dimensional symmetry that's breaking. So using that effective field theory mindset, we constructed the action just kind of by guesswork. Yeah. Guesswork meaning you identify the appropriate set of modes, then you just write everything down in a derivative expansion, and then you put coefficients A1, A2, A3, and then you just do an explicit computation and you fix these coefficients.
You gave us a talk.
And I gave a talk 2 years ago on how we did that process. Today I'm going to just derive it for you.
So just one more question along the lines of Sandeep's question.
Yeah.
Normally in a path integral, you do path integral over off-shell fields.
Yes.
So from that point of view, even if you had squeezed that momentum, then shouldn't you have expected then from that point of view the path integral to be D minus 1 dimension?
Yeah.
I mean the complementary question.
As I said, everything is going to be on-shell in this talk. There is an off-shell part of gamma.
Like not even to 1 dimension. Is that what you meant?
I would think since we're off, I mean he got one reduction because magnitude is 0. Let's give him that. But there's one more reduction because of one shell. But normally we don't do path integrals over on shell fields.
Yes.
We do path integrals over off shell.
Yes.
So you'll tell us.
Yeah. This gamma has a real part.
3, like from 4.
Yeah, it'll be 3.
No, that's what you mean. Okay, your D was, yeah. Okay.
Oh, sorry.
No, I was confused. Yeah, please.
No, absolutely. I'm hiding something under the rug. The off-shell part of gamma is three-dimensional.
Okay.
The part that I'm going to be focusing on this is 2-dimensional. It's the one that comes from on-shell contributions.
Okay.
We have an upcoming paper that gives you the T plus 1 dimensional action, which reproduces all of them. Okay, now let me write down some explicit formulas, and then I'll derive the action for you. Okay, so first, here's the effective action. So the low energy fields are this phi, so the soft photon, the field that inserts an external soft photon. Okay, now just to be clear, this soft photon is clearly D-dimensional because it's an external soft photon, it's on shell, so L squared is 0. And I'm taking the 0 energy limit on top of that. So the only thing that the momentum of a soft photon can depend on is the direction. So theta phi. I shouldn't keep saying theta phi because theta phi will end up being the fields that I'm using.
And so polarizations here or no?
Very good question. The soft photon has one polarization. A radiated photon has d polarizations in d plus 2 dimensions because it's a vector of SOD. But the soft photon has one. Because there's a constraint.
Okay.
It's kind of the analog of what's called the Christodoulou-Kleinoven constraint in gravity. There's a similar constraint. It's essentially coming from the fact that FAB, in the absence of magnetic charges, at least, the field strength FAB vanishes at infinity. So on the boundary of a Cauchy slice, FAB vanishes. And because FAB vanishes, AB being the angular directions, because FAB vanishes, this means that the gauge field on the boundaries is pure gauge, is del A of some theta. And so you don't actually have A independent components. Again, A is the angular direction. So A runs from 1 to D. You actually only have one independent component, just one scalar field.
I suppose I was very stupid. I just wrote down a plane wave solution of Maxwell's equations.
Yeah.
And now I start taking k to 0.
Yeah.
In that, if I have e to the pi k, I said,
Yeah.
what
You'll
will I
find that
notice about? I
you'll
just
find that-
notice that it's
Yeah.
the case.
Yeah, this is actually done in
Okay.
some works by Sabrina and Andrea, where they worked out these conformal wave functions for all of these conformally soft wave functions. So in particular, this particular wave function for this mode is the one that if you want to look up their papers and you just set delta equal to 1 in their
So
paper.
I was being even stupider. I'm not even doing this. So I'm e to the pi kx epsilon mu. You know,
Yeah.
I do what Landau dishes.
Yeah.
And then I said, I take k to 0. What will I notice? I notice something.
Yeah, you notice that this constraint is true for k to 0.
Well, if I take k to 0, everything is locally pure gauge. So I'm just trying to see what algebraically I do.
Why do you say that if I take k to 0?
I would say, imagine the field strength goes to 0 because there are no derivatives.
Okay. So this usual statement that I can take del to A, this doesn't hold because it only holds if the boundary terms are 0.
Well, sorry, can I be more stupid and not think about that? I just write down, I know what Landau dishes have no boundaries. Okay, just write down the photon solution.
Yeah.
On that, if I took k to 0, I would get field strength 0.
Yeah.
Or for every node.
Yeah.
So from that point of view, could I see that the two photons have become one somehow? I mean, it's a big question. Locally, I wanted to see locally, not going to the mouth.
In like fixed Lorentz gate or something.
Yeah.
No, you wouldn't see it there.
I wanted to
Because it's actually slightly more detailed. The reason you won't see it there is because this fact that there's only one polarization instead of two, for example, doesn't hold if I have magnetic charges. So you have to put there's additional input. So just the solution by itself
will not.
know. You need to kind of know what's the matter content of the theory. In particular, if there are magnetic.
I see. So it's not some local state, it's some more thing. Okay, fine.
Yeah, I can put it another way, if you like this or not, is that naively, you have two polarizations and you have one theta. But if you try to write down the symplectic form for this theory, because you just don't have a nice degree of freedom counting matching, you only have one theta, and it has to have one symplectic conjugate, but you have two polarizations. And so the only way to make that what that's telling you is that the symplectic form is not inverted.
And what was theta again? Large gauge transformation.
Yeah, theta is the large gauge. It's the goldstone mode for large gauge symmetry. That's going to be my next field.
But I'm really sorry to give you so many
Yeah.
questions, but I'm still having a little bit of trouble. Let me ask you this: will your 2D theory be local?
No?
Yeah, okay, because see, it just could not have been local, consistent with integrating out the magnitude of the
Absolutely.
solid. Okay, so then I'm fine. Thank you.
Absolutely. Yeah.
These modes between mu and lambda, they will have a relationships, right? Like,
Yeah, we'll collapse down all of these modes to kind of a single mode, because as we'll see in this low energy, again, my assumption always is that mu and lambda, well, I'm always assuming mu is less than lambda, and lambda on top of that is less than every other energy scale in the system. So in this limit, what we'll end up finding that I can take, so let me just write it out. So in this regime, so I can take a photon which has polarization A runs from 1 to D, and it depends on an energy omega, and it depends on some directions. And I'm just going to install some some coordinate x on the sphere. So when my omega is between mu and lambda, I can effectively write this as 1 over omega. This 1 over omega is coming from the Weinberg pole times del A phi of x, or this phi is that phi. That's the point. So in this regime, when I'm taking mu and lambda to be very, very small compared to every other energy scale, and I'm taking the energy of the photon to be in this between mu and lambda, I can always replace my, let's say, creation operator for the photon by a 1 over omega factor. This is the soft photon divergence, and times the photon that corresponds to being soft. And here I'm assuming in writing it as del A of phi, I'm specifically assuming the absence of magnetic charges. Otherwise, you do have to keep track of the other, which is actually another project that we're currently working on about how to include magnetic charges into the whole story. Okay, so these are my basic fields for which I need to write down the effective action. Phi is the soft photon, and theta is the goldstone mode corresponding to the spontaneous breaking of these large gates.
Sorry, and here the energy was not quite zero, so where was polarization here?
No, it doesn't have to be quite zero. That's what I'm saying. So I'm delineating as long as it's soft. Yeah.
But there are two polarizations.
No, my definition of soft is now, so all soft photons have one polarization. So as long as the energy is between mu and lambda, I'm going to give all the photons to have a single polarization.
But there exist polarizations with that energy. There exist photons with that energy with two polarizations.
Those won't be
No.
pure gauge anyway, right?
In the limit when, again, I'm always interested in the limit when lambda is taken to be 0 and mu is taken to be 0. So
Okay,
that limit.
But before you
Finite
take
mu
the
and
limit,
lambda, before you take the lambda, yeah, this is not.
Yes. But then what was the correction due to that? Sorry, I'm just trying to understand why one rather than two. Just that one.
Isn't it the amplitude of the other polarization is suppressed?
It's a
Yeah,
press in
that's-
this mu.
Well, okay, why?
But I have a picture in space time. I have a nice picture. For you.
Okay.
It's essentially coming from the fact that the field strength vanishes at infinity.
You're saying the soft factor is given by one of the two.
Yeah.
Okay.
Well, can I ask, these aren't real photons, right? I mean, real photons have non-trivial electromagnetic fields, right?
Yes. These don't
pure
produce.
gauge,
Yeah.
right?
But it's pure.
The measurable
limit
pure
K goes to zero.
I mean, this is kind of subtlety going on here, right? Because somehow in K going to zero, you can replace it by pure gauge. Then we shouldn't expect two polarized. I mean, I'm just saying
Yeah.
there's a kind of break there.
I agree, but suppose we're taking the limit. Before you take the limit, there are two photons.
Yes.
And
Completely
then
true.
Before you take the limit, it's not pure gauge.
It's not,
Yes.
not pure gauge, but still this must be approximately.
Yeah. There's.
Right?
So
And
this
this
is-
statement must be approximately true. I was trying to understand how.
I mean, because the transverse traceless photons
Yeah.
are specifically not pure gauge, right?
Yes.
I mean, so before you
Again, I
it's the drop.
I like to think it in this language where you just think about FAB, the field strength. So this is the, again, here these are the angular directions. So this FAB is of course del A AB minor del B AB. Okay, and think of this as a function on some Cauchy slice. So I have some Cauchy slice sigma, and this is some function on Cauchy slice. At any generic point in the bulk on sigma, this is something non-zero. But specifically on the boundary, so when you take this limit, in the absence of, again, here, in the absence of magnetic charges, FAB precisely vanishes on the boundary. And then on the boundary, the gauge field becomes pure gauge. So the value of the gauge, away from the boundary, you always have two polarizations. But exactly on the boundary, you have exactly one polarization because it's pure
Those
gauge.
two polarizations in the bulk will effectively go away in the soft limit.
Yes, and this is seen already in the soft fact.
Is roughly the point is that the conjugate momentum is the electric field, right?
Yes,
So
exactly.
Send omega to 0 and those sort of become degenerate, but these boundary modes still continue to have a synthetic expression.
Yeah.
This is.
Yeah.
Because theta, the action for theta must depend on what hard part of the field.
No, I'm going to write down this action will be not dependent on what other particles are. The other particles will come in from this Wilson line, which of course depend on theta. Because I'll have to address the particles with Wilson line. I'll tell you what they are. Okay, let me write down the action. Let me just get to that. Okay, so here's the full action. This is alpha ddx del phi square. Then there's I. I'm not going to write down all the explicit numbers and factors, but ddx del phi del theta. It's a very nice and simple Gaussian thing.
Just remember, so phi was of course this.
Phi is this field that's appearing here. Yeah, theta is the field that I wrote here. Theta is the field that you take the gauge field. You take the A component of the gauge field, so the angular component of the gauge field.
That is del A.
And you evaluate it on the boundary of any Cauchy slice. Take your favorite Cauchy. So it's a t equal to constant slice and evaluate, take the R goes to infinity limit. This is del A of theta.
The theta is the pure gauge mode,
Theta is the pure gauge.
and phi was what? I mean, physically?
Phi is the soft photon mode,
Nice. Pure gauge mode and the soft mode.
which are symplectic conjugates of each other. So you have to keep both of them in the theory.
Nice.
That's why you can't integrate out one and keep the other.
Nice.
So this you got after integrating out the bulk.
Yeah, I've integrated out. Well, actually, that's what I'm going to show in this talk. Is that's how you get it. But actually, in the original paper, we guessed it. We didn't actually do any explicit integrating out. We just wrote it down. But yeah, in what I'm now going to show you, and for the remainder of this talk, is that if I take the bulk D plus 2 dimensional gauge theory action, I integrate out all the hard fields, I integrate out all the radiative photon degrees of freedom and keep only the soft modes, you'll get this.
What was the tilde notation?
Yeah. Let me explain all the notation here, everything here. So alpha is the IR divergence. So alpha is E squared over 8 pi integral mu to lambda. So this is where the mu and lambda dependence shows up. D minus 5. Where D, capital D is the bulk dimension. So here from this you can see that in 4 dimensions this is a logarithmically divergent quantity. But I'm doing everything in general dimension just because there are many features that you see only if you go to all dimensions. In higher dimensions, it's totally finite. So there's no IR divergence, it's in greater than 5 dimensions. Greater than or equal to 5 dimensions. But in 4 dimensions, you get something that's logarithmically divergent. And 3 is even worse. Okay, that's what alpha is. E is, of course, the gauge coupling. And this tilde notation corresponds to the shadow transform. So it's a transform. Let me.
That's probably what makes it non-local.
This is the non-local. This is where the non-locality is coming. So the shadow transform, and I'm just going to write it down for this particular case for a vector field. So this is a vector because it's a del of something. So I take a vector. The shadow of the vector is defined to be ddy IAB minus, usually it's d minus delta, where delta is the dimension of the origin of this operator CB y, but in this case the dimension is 1, so it's d minus.
And IAB is standard.
IAB is the conformally covariant tensor in a CFP, so this is delta AB. Yeah, this is a standard XA. So this is actually a very standard thing you do in CFTs. It's so just to explain where this comes from. The shadow transform is kind of the unique non-local integral transform that maps a conformal primary operator of dimension delta and representation R of SOD, whatever that may be, to another conformal primary. This is also a conformal primary. It doesn't look like it, but this is a conformal primary with dimension D minus delta and the same spin. So the SOD representation remains unchanged.
This is just the 2-point function of
It is just the 2-point function of a current.
that's why it's conformal.
That's right, exactly.
In the ambiguity that you wrote in terms of this line, what happened to the graph?
In the one?
In this particle that you put
Yeah.
the soft factor, what is happening?
Yeah, so I have to do the full path integral over all my soft fields, which includes phi as well as theta. So here phi s just means the collection of all soft fields, and here the collection corresponds to phi and theta. So I also need to give you some extra information. So I've already told you what phi is. So for each of these soft photons, I just insert a factor of phi. And for each of these u's, I insert Wilson line. And you can actually work out what this Wilson line has to be in many different ways. In fact, in the original paper, again, because a lot of our motivation was just to guess the right thing and just go with it. So we guessed what this UI has to be. In this paper, in 2405, we actually showed that the guess that we made here is in fact the Wilson line. So it doesn't look, what I'm going to write down doesn't look like the Wilson line dressing, but in a subsequent paper, we've shown that it actually is. So the way we guessed it, again, as usual, we are always guided by symmetries. We just look, we know how hard particles are supposed to transform under large gauge transformations. And we know that theta, under large gauge transformations, theta goes to theta plus epsilon. It's the goldstone mode for that symmetry. So I can just engineer what U has to be so that the hard modes have the right gauge transformation properties, large gauge transformations. I can just engineer what that is. And it turns out that these U's for each particle I is given by rather nice formula. It's the exponential of I qi. So the charge, the U1 charge of that qth particle. Then I do an integral. So this is, remember, this is Ui at, it's a function of the momentum of that particle, whatever that momentum is. So here I integrate over ddx and theta x. And to go from x to pi is I use the ADS bulk to boundary propagator. So this is there's a bulk point which is p. Remember, this p satisfies p squared is equal to minus m squared. So therefore, it defines a point in Euclidean ADS space. And so there's a bulk to boundary propagator for that space-time. And I take the bulk to boundary propagator with delta equal to t. And so the bulk point is given by p, and then x corresponds to the boundary point. Like this way. That's everything you need to know about this entire formula right here. Okay.
This is pretty complicated. I mean, this is nowhere near a real tragedy.
No,
this is
something crazy. But yeah, what you can show is if I literally just take a particle like in d plus 2 dimensions that is moving along some curve gamma, and I attach the usual Wilson line, which is given by e to the I qi integral gamma I a. And then I integrate out the radiative modes. Remember, I'm only keeping track of the soft sector. Then this reduces that.
very complicated. Okay, yeah.
Okay, so this should, now you can compute everything you want. I've given you this action, so I've given you this part. I've given you all external soft insertions, which just corresponds to phi. It's a field in there. I've given you what U is, so it's just something linear in theta. No phi enters over here. So you can actually compute this full path integral trivially because it's a Gaussian path integral. Everything is quadratic. That's quadratic. You know, these are linear insertions in theta. So it's super trivial to just compute.
Sorry, perhaps this would be the bulk to boundary propagator for what mass field?
For whatever the mass of this ith particle is. Because the idea is that there's an ADS hidden inside this because the momenta satisfies pi squared is equal to minus mi squared. And this is the defining property of how you embed ADS in flat space.
Oh, you mean this is that hyperbolic?
Yeah, this is the ADS. So yeah, that's the light cone, and then p squared is minus m squared. It's some Euclidean slice. So this is Euclidean ADS with radius mi. So you take a bulk to boundary propagator in that ADS. You take the delta, the scaling dimension, to be d.
D. Okay, so delta corresponds to D.
Delta corresponds to d, and then you just take that bulk to boundary propagator and plug it in.
And the Wilson line just couples additively. E goes to a plus d theta.
Yeah.
Just how it transforms that the gauge transformation.
Yes.
And it's non-trivial because the gauge transformation doesn't vanish at the boundary.
Exactly. That's what all the non-trivialities are. Even this basic idea that we think of you take a derivative and the Fourier transform of a derivative is the momentum. That's not true if the function doesn't vanish at any. Because the way we usually do this is that we do the Fourier transform, then we integrate by parts. We take the del and by integrating by parts give you extra boundary terms if the function doesn't vanish. So that's where all the subtleties come.
This E is not the Coulomb field created by insertion of charge.
This is the full bulk field. So it's a Coulomb field produced by everything. And then we just have to work it out.
This is really vital, yes. Right? This. I see.
Okay. Okay, that completes the first part of my talk. I haven't started yet with the actual paper. Okay, so everyone's happy with this? Everyone understands all the symbols on the board? Okay, now I'm going to try to prove that that's the action. You know, there's several features I need to be able to reproduce. There's a non-locality that I have to reproduce somehow from the bulk action, which is local, of course. And there's a factor of I, which I have to reproduce. You know, there's a relative factor of I. That's even more problematic because you could have argued that, well, the bulk action is Lorentzian. So the path integral is given by e to the is. And here I'm writing down the effective action as a Euclidean action. So there's a e to the minus I. So that could explain that factor of I. But the problem here is that there's a relative factor of I, not an overall factor of I. So I have to explain that also. Okay. Okay. Okay, yeah, and of course I didn't say the whole point of this action is that if you use this action to compute that path integral, you reproduce Weinberg's soft theorem, you reproduce the whole Feynman diagram computation. And it's a nice way to reproduce it because, again, you know, it's not that hard to do in QED because you can just do the Feynman diagram computation explicitly. But this is so much more trivial. It's just literally just a quadratic action. So it's much easier to solve. But the claim is that you completely reproduce all IR properties in the bulk. Okay, except, and I'm still lying to you a little bit, except you really don't because there's actually another term. So I didn't write down what exactly gamma was. So it turns out gamma is given by alpha times ddx, and there's, you know, the J, the soft factor that I wrote down, for which appears in Weinberg's soft factor. So it's given by this guy. And that's kind of where this term is coming from. This term kind of replaces this piece. And there's actually another imaginary piece, or the imaginary part of gamma. And this imaginary part is basically where it's coming from doing the loop integrals in that Feynman diagram, but it's coming from off-shell loop integrals. That's the on-shell contribution. That's the off-shell contribution. And this imaginary part is not given by a d-dimensional integral. It's given by a d+1 dimensional integral, exactly as expected. So the effective action that reproduces this imaginary part is not yet known. But I think given the fact that I'm going to derive this for you, there's going to be one term where it's clear that that's where it's coming from, which for this talk, I'm just going to drop. But in some future paper, we are trying to prove that that term actually does give you the imaginary piece. Okay. Again, I'm not, this is a much more complicated formula to write down, but it's not a d-dimensional integral. That's the point. It's a d+1 dimensional integral.
So it's coming from some arguments?
No, it's still coming from soft modes. So here, when I do this integral, remember, there's an L. This is a loop integral. So the loop integral, I have to integrate over d+2 momenta, right? One of these d+2 is reduced because I'm looking at the soft limit. So after taking the soft limit, it becomes a d+1 dimensional integral. Okay. Then I can break up the integrand here into an on-shell part and an off-shell part. So on-shell is the one that's proportional to delta function of L squared. The on-shell part will reduce the dimension by even one more. So I'll get a d-dimensional integral. And that's this d-dimension. Then there's an off-shell part, which corresponds to a d+1 dimensional.
And the on-shell part is not trivial because you've got some delta function, some imaginary part or something.
Yes, and that's where the I is coming from also. Yeah, precisely. Okay? Okay. Okay, can I ask how much time I have? So I'll know how fast to go.
Yeah, until lunch.
At least.
An hour? Okay. All right. Okay, let me also just point out that all of this fits into this the reasoning that, Shiraz had a nice paper recently where you think of the S matrix as, and Omkar and many others, there were other, but yeah, the idea is that you can think of the partition function in a, you take the bulk partition function as some function of the boundary values, of course, which at tree level is simply given by computing the action on shell as a function of those boundary values. And that, is related to the S matrix in some way. So there's some boundary action, effective action that you can use to compute S matrices. Of course, the soft part that I was showing you here is one feature of the S matrix. So you should expect that boundary action should reproduce that feature. And indeed, that feature is exactly this. And the proof that I'm going to outline in the rest of this talk is essentially showing that you just take the bulk action, you evaluate it, you evaluate the path integral as a function of boundary fields in the usual way, but now keeping only the soft sector, keeping only the contribution of the soft fields, and you'll get this. So it fits into that entire formalism.
And the shadow transform is sort of like fits into what Shamik pointed out about.
Yes.
Yeah.
Though in what I'm going to show you, it comes about in a really weird way, which we haven't fully understood.
But if you just do Shamik on this, it would come.
So okay, we know from like other reasons why we should expect the shadow transform here, but in the derivation, the way it comes about is a bit weird, and I haven't understood it myself. But again, the idea is that if you tell me beforehand that the action is going to be non-local, then I can guarantee that non-locality has to be a shadow transform because it's the only thing that has the right symmetry transformation property. So there couldn't have been any other answer. This is the only thing that it could have been.
But just to ask this again, in our paper we had this inverse LSZ transformation.
Yeah.
Which was that you give me the S matrix and I'll produce for you the Green's the action as a function.
It's coming from the Green's function.
The Green's function.
Yeah, the whole shadow is coming from the Green's.
That is a shadow transform.
Yes, that's exactly it.
Yeah.
That's exactly it. Okay, now where do I start? Oh, I didn't write down what J was. I haven't yet told you exactly what this soft factor is. But of course, by the soft factor, I mean Weinberg soft factor. So if you maybe remember it from QFT, but I'll tell you what that is. I'll give an explicit formula later in the talk when it comes up. Okay, so here's what I'm doing. I'm doing something super simple. The basic idea is very simple, but then when you get into the weeds of the calculation, that's tricky because we have to pull very non-trivial results from other papers, from multiple other papers. So it wasn't obvious to see the connection outright. But what I'm going to do is very simple. So the starting point is I'm going to start with any bulk action. So I have some bulk action defined in p+2 dimension. And of course, it has, at low energy, it has the Maxwell term. But then it can have anything else. And this could be some matter Lagrangian. It could contain f to the 4 terms. It could contain QED, whatever you want. And then this is going to be crucial because again, everything we're talking about are like the boundary contributions. There's also boundary terms in the action, which we have to keep to have well-defined variation points.
Sorry, one question.
Yeah.
Just to interrupt, I'm sorry. But suppose everything was in a big box, but a box. Everything you say will go through. Yes or no?
Yes, there won't be a K to 0 limit because it will be cut off.
Yes,
by the box
but the
size.
soft mode will still exist.
Yeah.
Okay. Yes.
And then you impose boundary conditions on the box, on the boundary of that box.
The boundary conditions are a restriction of field strength on box.
Yeah.
Box is 0.
Yeah.
And then everything here.
Everything goes
It's
back.
not. Yeah. There's no sign. So that's somehow for me a nicer way of thinking.
Yeah, but the fact that this box is infinite size is where this universality is coming from. So the 1/r effects, which will not be there in a
Infinity
finite.
compared to what? Compared to, let's say, the masses of the scales, energy
Yeah,
scales.
okay, yeah. If you take the masses to be much larger,
Or the energy scales and these things, then we could just do it, right?
Yeah,
And then we can't fool ourselves with it.
yeah, absolutely.
Isn't mu the size of the box?
Roughly, mu is the size of the box.
Yeah, but I was just wondering in space if we just put a box. We put a box, we put our boundary conditions at some finite region.
Yeah.
And then we quantize the theory honestly.
Yeah.
I mean, I feel then there's no room to fool yourself about what is a large case or what.
No, I mean, to be clear, yeah, okay. I haven't done it for a box, but this whole story that there's this reduction in the number of degrees of freedom is precisely coming from quantizing Minkowski spacetime, not in a box, but carefully.
But this carefully is what I mean. I mean,
Yeah.
for me, carefully really is a box.
Okay.
I mean, because otherwise you can invent new rules, right, at infinity, and somehow.
Okay.
So your point is, just so I understand it, you just put it in a box, impose the fact that the field strengths vanish, and then, if needed, add boundary terms.
Whatever,
Yeah.
say explicitly whatever.
Yeah.
And then,
So yeah, which is already what we did for Minkowski, where you want to do it for a box, you have these boundary conditions, you write down the symplectic form of the theory, because you want to write out the Poisson brackets. You'll find that the symplectic form is not invertible, so there are no well-defined Poisson brackets. To make it well-defined, you need to reduce the number of degrees of freedom for the soft modes by hand. You have to enforce it, otherwise you don't have a well-defined phase space that you can quantize.
But now also the soft mode, I mean, it's discrete, right?
It's discrete.
It's discrete.
Absolutely.
You can identify one mode and say, this is my
Yes.
soft.
That is
It's not some
absolutely.
continuum and.
Yeah.
Yeah. Okay.
Yeah, in fact, that's a nice way. That's definitely a nice way to look at it. Like the way to think about it then is that it's discrete, and yeah, if I have some momentum which is like depends on n over L of the size of the box. So for every momentum with positive n,
Yes.
it's symplectically conjugate to negative n.
Yes, all those are calling hard.
And all of those have two polarizations.
Yes.
Now you might ask, what happens to the mode with 0n when n equal to 0, and that is symplectically conjugate to theta.
Yes.
But then there's only one theta.
Yes.
So you can't have two modes with n equal to 0. So you must have only one mode.
Yes.
So that's the reduction. of
Yeah.
that.
And then we just isolate that one n equals 0 mode, we can figure out the best.
Absolutely.
And then it's very clean, right?
Absolutely.
Does this also happen for fermions, like the zero mode has 0 plus?
Yes, it also happens for fermions. For massless fermions.
and actually, probably just to, this is a side physics feeling, but actually, in terms of entanglement, probably you will repeat what Shiraz is saying. If you just impose the electric fields on the boundary to be fixed, they don't even have to vanish, right?
Yeah.
And that's the electric centered. So
Absolutely.
that's a good way to think for anything. Yes. Okay, go ahead, please.
Okay.
Thank you.
So I'm just going to start with this action. And then I'm going to evaluate it on shell after imposing some boundary conditions. Okay, but more than that, because I'm only interested in the soft contribution. The whole point of this is to extract a soft effective action. So, and this is why this whole problem becomes so simple, is that in the soft limit, only the lowest derivative terms in the action contribute. Because as you add derivatives, that adds extra factors of energy. So only the absolute lowest derivative terms that are present in the action are going to contribute.
One last interruption, I'll shut up.
Yeah.
But now your boundary conditions have to be such that it allows this n equals 0. And is
Yes.
it true that in ADS that is not allowed? I was wondering if I got ADS as a box.
No, you can still allow this mode, I think. But you can't allow this mode, the radiative mode, because ADS you have to impose, well, we typically impose reflecting boundary conditions. We don't have radiative flux leaving which is where this phi is coming.
I was thinking that there is usually a mass gap for a conformity.
ADS gives a IR cutoff.
Right. So that the soft mode goes away. Right?
The soft mode goes away. But of course, this Goldstone mode is still can be present as boundary gravitons, for example, in ADS3.
But there is no state at 0 energy.
There's no state at 0. Yeah, absolutely.
So in some sense, that's a boundary condition that you don't do.
Yes.
Okay, fine.
Isn't that like initially not for the field strengths?
It was very similar because
Yeah, but we're not going to impose duration because that's the point. That's why we have to be careful about this boundary term.
But somehow in ADS we've got a lot of experience with what is good and what is bad.
Yeah.
But I was just wondering whether that boundary condition is different from what I was understanding your boundary.
I think it's similar, apart from, you were saying restriction of field strength on boundaries. Yeah. That's what I was saying.
Yeah.
Restriction of field strength on boundary is 0. Now, then the other boundary condition could be restriction of gauge field on boundaries.
Yes.
Yes. But that will be different. For
Okay.
him, it will be
Yeah,
quite
let me
different.
write down the boundary
See,
condition.
I feel that his
Yeah.
story was
So here's the boundary condition.
field strength imposed to be 0.
But were we allowed to do it in ADS to put this first one not the second one? I thought we had very good ideas.
It's the other.
Sorry. I think you can for in some dimensions. It's this is four dimensions for
Maybe
gauge
for
fields,
some fields.
But not in 5, right?
but not in 5. So gauge fields it's 4.
Ah.
I don't think you can do this for the
It's
metric
the alternate
at all.
quantization, isn't
It's
it?
the alternate
quantization.
Concentration consistent only. Yeah.
Yes.
Yeah.
But you can do it. You can do it for massive scalar fields if they have mass between minus d squared over 4 to minus d plus 1. So that's some.
Exactly.
It's precisely the alternate
Yeah.
quantization.
Yeah, that's what I see.
Which is like some.
If you could, then you could.
Yeah.
Okay, so I'll just write down, I'll start off by writing down, just to be precise. So here, the point is that Minkowski spacetime has a rather complicated boundary structure. There's a square plus, and I'll just join, there's an I0 sitting up there, which is a I plus. Okay, then this is just R equal to 0. So the origin. Then on this side, I have a I0, which is spatial infinity. Then I have I prime minus, and I have I minus. I need to tell you the boundary conditions on all of these boundaries. And the idea is that on I0, I want to impose Dirichlet boundary condition. So here, nothing can ever reach I0. So I0 is very much like the boundary of ADS. So here I want reflecting boundary conditions. So on I0, I'm just going to literally impose that A is fixed. So if I take a variation and on I0, so I just completely fix the gauge field. Here I want flux to pass through. So I want radiation flux to pass through square plus and square minus. So the appropriate boundary condition there is that the variation of the normal on I plus minus and square plus minus. So on both of these should be equal to 0.
Oh, so you're saying the kind of box I never mimics what you want.
Well, you can do that. So if you can do this box where here I impose Dirichlet and here you impose radiative, that should be fine.
Okay, so okay, fine. Thank you.
That vertical direction is not time.
Yeah, this is time. This
In
is
your
like
box also. In your box.
Oh yeah, in the box also, vertical is time, and I'm assuming this is kind of really far off. You can impose these boundary conditions by just saying on these boundaries, you have that boundary condition, and on these boundaries, you have this boundary.
Then it's also different from what I thought. I thought on the spatial ones also, you were fixing the field strengths. That's not the case. Huh?
No, I think just to say physically, the difference between the box and everything else is that no matter how big you make the box, if you wait long enough, there'll be reflection.
Yes, which you don't want. That's why it's very important.
Yeah.
There's another reason scattering is hard in ADS because things can always rescatter.
So I interpret, anyway, if you go on, I interpreted Shiraz's point as saying on the spatial boundaries of the box, we would.
That's what I was saying. That's what I was saying.
And that's
what I was saying.
Well,
And he said
actually-
that's a big difference from Minkowski.
But maybe, yeah. Actually, how to think? Maybe, yeah. It would not be good to impose reflecting boundary conditions in a finite box because then you can have.
But it's
Well, you could.
initially for the gauge field.
Oh, this is Dirichlet for the gauge.
This is, but not Shiraz.
No, but I think you can do it as well, but you have to make sure, you have to insist that your limit is that this spatial boundary is always much further off than the time-like boundary, so that any reflection will never cause any new scattering.
Right.
That's very right. Yeah, you can't have like a box like this because then I can have a lot of multiple scatterings coming.
So it's like omega is you want, because you want a soft mode, you want K to be 1 by L,
Yeah,
but you want omega to be much larger than.
Yeah.
Something, right?
yeah.
Okay, interesting.
Okay.
What is this anything data? What does that mean?
Or just means that I'm fixing, so what data I'm fixing on each of these things. So here I'm going to just fix what I mean by A. I'm just going to tell you what A is. That's a boundary condition. So I'm not allowed to vary that. So that's one of the things I'm just telling you beforehand. So in other words, when I do the path integral, I'm going to do a path integral over some field configuration space. In that field configuration space, the value of A on spatial infinity is held fixed, and I'm integrating over all possible functions A with that given value. And then here I'm fixing the normal component of the field strength. The normal component being the radiation. So I'm kind of telling you what the radiative data is, and that's what defines an S matrix, right? S matrix is you tell me some data on square minus, you tell me some data on square plus, and then I tell you what the overlap is. That's the transition probability.
Because there's this constant flux going out of this.
Of square plus and square plus I minus, square plus square plus, square plus square minus, I plus and I minus. Yeah.
Is it locally or like?
Locally at every point. I'm not doing any integral. So I'll have to tell you what this function is. That's the scattering problem. That given some in data and some out data, what's the probability that scattering happens? So I need to clearly then part of that definition is I need to tell you what is that in data, what is the out data. So those are the things I'm fixing. And then similarly, I need to fix this. This is where the large gauge mode comes in. So theta is one of our boundary data that I'm inputting. Okay, so this is the boundary conditions I'll be imposing for my problem. Let me write it there. Delta A I0 is 0, delta IN F on sigma plus minus. So these are two Cauchy slices. I'm just going to denote kind of roughly this Cauchy slice as sigma plus, this Cauchy slice as sigma minus, and of course I'm interested in taking the limit where sigma plus and sigma minus go out to square plus. Okay, so those are my boundary conditions. And given these boundary conditions, I can now work out what the boundary term is, because I need to have a well-defined variational principle. So this is the usual Gibbons-Hawking type construction. And you can follow that Gibbons-Hawking idea. And write down what the full action is. So now let me just write down the action I'm going to actually work with, because remember, I've told you now two things. This is of course the general action. I'm only interested in the soft sector. And the great thing about the soft sector is that I can get rid of any high derivative terms, because every derivative adds a factor of energy. So I can just reduce it down to the quadratic pieces. So what is the lowest derivative action that I'm going to work with? It's going to be the Maxwell term. That's the lowest derivative p squared f wedge star f. Then I'm integrating out also all the matter fields in the theory. And so every time I integrate out a matter field, there's going to be an effective coupling that appears. And that effective coupling, again, at lowest derivative order, is well known. It's A wedge star J. It's just the coupling of the gauge field to the matter current. So this matter current is whatever I get after you integrate out all the massive fields. Okay. And then I have boundary terms, which I can derive using these boundary conditions. And they're very simple. They work out to be 1 over t squared. One term on sigma plus, A wedge star f, and then another term on sigma minus, because I have these boundary conditions both on sigma plus and sigma minus, A wedge star. And I don't need to add any boundary term on I0. The Dirichlet variation problem is automatically true without any extra boundary terms. Okay, so the goal of this talk is to just take this action evaluated on shell with boundary terms. So since I'm doing that, the first step should be to tell you a little bit about solutions to Maxwell. And now this is Maxwell theory, literally just free Maxwell's theory coupled to some current. So you guys must be really familiar with this theory, but let me just
make sure the mu here is what?
Oh, not mu, this is the M and R.
The full 4D then.
We have R1D plus 1. And this is a sigma plus, where sigma plus minus is chi plus minus union I. So it's the Cauchy slice at infinity.
And just so I understand, sorry, J here, how am I supposed to about J? The world line, not the. What is J?
Yeah, you can think of it as the world line. This depends on your matter content of the theory and whatever my matter insertions are in my path integral. But for example, this can be, for example, a scalar. I can have this term in there, right? And then I could be scattering, for example, these charged scalar particles with some momentum P1, P2, P3, Pn. And then I integrate out all these matter fields. That's what the hard part of the scattering amplitude will give. And I'm not bothered about that. So again, that's very theory dependent. But the point is that after you integrate all of that out, there's going to be a leftover piece, which will simply tell you this is A. coupled to the background current generated by the particles that are moving out in the S matrix. So this is, you can literally think of this as endpoint particle conserved currents.
So the idea is to compute this as a functional of J.
As a functional of J, of course,
And
theta and phi. This theta here and this phi.
I once aware of. So
They're in the gauge field. I'm going to tell you now.
Okay.
Of course, they're all components. They're various components of the gauge field.
Okay.
So those are the things I'm holding fixed, and then I'm integrating out over everything else.
Oh, I see.
From this box point of view, those are the only masses.
Those are the only masses. Yeah.
Oh, sorry, why doesn't this assume that
Very nice.
A can't? Why doesn't this assume that the A can't kick J back? Like,
It can, and it does. I'm saying after doing all of that, you have some final current, and you just put whatever that is in.
You do that self-consistent.
Yeah,
You find
that's
the function of J,
self-consistency.
and then you find the solution to the equation of motion of that R.
but you're trying to derive the influence of the soft modes.
So J should be thought of as off-shell.
Yeah, J is offshore. Okay, so let me process each of these terms one by one, and maybe I'll just tell you where everything is coming from. This term, these two terms together, will give me this piece, and it will give me the UIs. You remember the Wilson line dressings that we had, the U1 to UM? So we had this whole product. So this whole product and all of this is going to come from these two guys.
But the Wilson line was along Wilson lines of the charge particle.
Of the
right?
charge particle.
So isn't that like the A dots?
No, doesn't come from. It's secretly in there because those Wilson lines they generate a Coulomb field, and that Coulomb field is the thing that will
So Wilson lines of all the other particles on this.
yeah,
Right.
that'll come from this. This will just drop out. It will simply not contribute. In the soft limit, it will not contribute. Of course, it's there in the actual theory. The full effective action really cares about this. In the soft limit, it doesn't matter. And then this term will give us that.
No, but the fact that A reacts to the Wilson line is coming from some term in this action.
Yeah. So that's when you solve the equation. That's part of the solving.
Fine.
But
But
then-
for the solving that A star gave was crucial.
Yes, absolutely. Yeah, 100%.
Yeah, I get it.
Yeah, okay, so the kicking back part is done taking care of outside this, and this is I think so. There is an approximation.
Yeah, so I'm going to the next part of my talk will be to tell you about solutions, in which of course this J term will be very crucial. Then once I get the full solution, which we've kept track of all the back reaction and everything, then I'm going to plug in that solution into the action. Then my claim is that you take that whole solution, plug it in, these two terms will give us this piece and that piece. And this term will simply not contribute. It'll contribute in finding the solutions, but once you have the solution and plug in the solution here, it will not contribute. And then this term will give us that.
How do you think of this as square?
There's a dependence anyway on J because it's an
Yeah.
on-shell quantity.
How do you think of this as just squaring?
Yeah.
I complete the square.
Yeah, I want to complete the square for everything except the soft modes
Of course.
because I'm not integrating out the soft modes.
But when you're computing when you're computing the back reaction, are you taking into account soft modes or not?
It's a completely self-consistent set of equations you have to solve. So yes,
On the hard particles?
On the J.
I think the soft modes will be crucial. Because this log R potential is affecting all the way to it.
Okay. So can we see why the factor I is coming from the factor we said?
yeah, it'll come from this factor because this is the Lorentzian path integral. To define the Lorentzian path integral, you have to introduce an I epsilon prescription. I epsilon prescription will give us. And we'll see from there that there's clearly an off-shell prescription, contribution, which is a d plus 1 dimension integral, which I'm going to drop for now because it's not what we discussed in the soft effective action, but of course it's important for the full story.
Just one question. I mean, Shivansh. I mean, since Prahar has so much material and he's also here on Thursday, I was wondering if instead of him rushing through, we could continue and we could have your thing next week. Is that okay with you? Or is it?
I will really clear.
I mean, next week is what?
End of November.
That's
not December.
I don't want to take as if that's okay.
Is next week beginning of December?
Beginning of December. It's also the week of Shreya, isn't it? It's likely busy, but next Thursday is unbooked as well.
Is that the?
Yeah, but then after that, I'm like gone because mid-December onwards, life is impossible, right?
Are you going to NSL by the way?
Yeah.
Okay, so if you don't mind, just since we have Prahar only for a few days, and since this is so clear and I'm finally understanding things I've never understood.
Feel free to say no. I mean, really, I don't want to take anyone else.
Yeah, I'm around. You don't need me, but
Okay, then if that's okay with organizers, Prahar doesn't have to hurry.
Okay.
If you don't mind.
I don't mind, but you guys may be bored listening to all these technical details because I feel like it's going to go into details at this point.
No, but it's really nice. I mean, I feel that. I mean, so now since we have more time, I can insert. Okay. Okay. So would it be consistent to set theta equal to 0 and to kill the soft mode?
Yeah.
As quantization.
As at the level of quantization, you can remove theta, you can remove the soft modes completely, and you have.
So then I feel that ADS is doing that. It's removing theta. I mean, the thing we normally do. Yes. It's removing theta. It's removing the soft mode. So how do we know that's not the right thing to do?
I think that is the right thing to do. That's what the Faddeev-Coolidge dressed scattering amplitudes are doing. Because the Faddeev-Coolidge dressed amplitudes don't have any soft theorems attached to them. They have no IR divergences attached to them. They're completely IR finite and the soft limit is just 0. Well, not 0. There's no 1 over omega pole, right? So and then the argument is that in gauge theories, those are the correct kind of basis states to work with, not the free electron. All of these IR divergences are coming from coming from the fact that I'm making the incorrect assumption that a free electron is a well-defined state in QED.
So let me just ask one more. So I've got this box, spatial box like Sandeep wants. We've got this box, we quantize.
Yeah.
All modes with non-zero momentum are unambiguous, right? You know what?
Yeah.
The question is what to do at zero.
Yes.
Now it seems to me that you're telling me, and please tell me if this is wrong, that you're telling me that there are two equivalent quantizations. One in which I just drop all zero momentum. Theta is frozen on the boundary. The zero momentum photon I just throw away. It's not in my phase space. That's one quantization. Another one where you keep theta and this one polarization.
Yes.
Both is the claim that these are two independent, consistent quantizations of this theory. I'm putting it in a box so that's very, for me it's clear.
Okay, let me ask the following question. If you have two independent theories, they should give different answers.
Independent quantizations, yeah.
Okay. Independent quantizations, therefore independent. Different physical theories, right?
Yeah.
I mean, is there a sense in which you have two different S matrices, both of which are well defined but different? Both are unitary, but both are different. Is this true or not? I mean, this is what I've never understood about all your inference. You guys, because of course I know it's very subtle, but partly the S matrix itself is not always well defined. Then how do you ask the question?
Exactly. So first, just is this true that there are two independent? Put it in a box.
Yeah.
Throwing away the zero modes or keeping them are two independent. Is that true?
Two independent, not equivalent.
No,
but independent. I think
independent, both consistent. As far at least at the level of.
Would you say that in three dimensions, like let's say if you're transcending theory in 3 dimensions in a box, so setting theta to 0 would be like setting the WZW between the figures, right?
Yeah.
So that's not standardly what one does.
Yeah.
And now I don't know what the reason is. Is that
It's somehow thinking in terms of factor was first order with the so that it was setting that zero setting like both putting too many boundary conditions.
Is that right?
I think so. If you think in terms of particle, this paper by Cyber, they may do it carefully, not 100% carefully.
In the box.
Yeah, in a box, and they cannot do it. Here, I suppose is what I was asking. It looks like you can
do it.
or not. I don't know.
Yeah, sounds right. Because there is theta and then there is a normal component.
Yes, exactly.
Yeah.
I guess you could say.
And now coming to say,
so
if
now
that is the case, coming to Sandeep's question, is it the case then that your final answer will not care once you take some limit? Once you take the limit, the box goes to infinity and you keep your scattering momenta fixed.
And doing the dressing appropriately. In the theory which has the zero modes, the point is that limit, taking the infinite limit, is not going to be well defined because you don't get a well-defined S matrix when the box is infinite size, unless you kind of do the Faddeev-Coolidge dressing, right? So then you have to include the zero modes in that description. And then the question is, does that dressed S matrix match the
undressed S matrix for the removed one? I mean, if that is the case, that's very beautiful, right? I mean, that tells you, do you give up on all this Faddeev-Coolidge, just drop that mode. I mean, it sounds too simple.
Isn't that because it's not that that's not completely decouples from the Hamiltonian, right? The Hamiltonian has a square term, like the normal component of the electric field square.
But isn't that zero because the phase?
This is the boundary value of the electric field.
Yes.
Yeah.
Sorry, K is, no, the normal component being the radially box.
Yeah, but I'm saying, are you talking about just the mode?
You're saying.
Yeah.
We're talking about zero mode.
Let me ask I'm sorry, I'm never really worked on the infrared issues. Let me ask you this, all I really know is, even if you have infrared issues, if you ask about inclusive cross-sections,
Yes.
then you always get sensible
Yes.
answers, right? And is it, if you ask about inclusive cross-sections, that the difference between Faddeev-Coolidge or whatever else goes away?
Yeah. The S matrix, the cross section you evaluate using the Faddeev-Coolidge dressing is the inclusive cross section that you evaluate so at the level of cross sections, they're both definitely.
S matrices are ambiguous, but by the time you go to cross sections,
Assuming so in the Faddeev-Coolidge case, because the S matrix itself is well defined, so you don't need to do any inclusives. You mod squared, that gives you the cross section. You know, in normal QED, the standard S matrix is I divergent to mod squared, then sum over a bunch of stuff. Those two things are the same.
Then they agree.
But if this is the case, then it will tell you that this Faddeev-Coolidge thing is unitary. So it will be a big payoff, right? Because the other thing is clearly unitary.
Yeah, well, except that the dressing has both real and imaginary piece. And
no, so okay, fine, forget Faddeev-Coolidge. I'm saying the second thing is clearly unitary. Right? If you've thrown away the zero modes, then there are no problems. So it's just a normal S matrix. State to state will be unitary. Right? So that thing will define by itself a unitary S matrix, I think. And if that is the case, then whatever else you do otherwise should be tuned to match this thing. I know it's very
simple. It's Faddeev-Coolidge where you keep this mode or you don't keep the zero mode of shadows.
Faddeev-Coolidge, of course.
I understand the terminology.
Faddeev-Coolidge never talks about this theta mode, but kind of, and he never talks in this language. They never talk in this language anyway, but they kind of talk, they keep the soft mode. They dress it with some integrals over the creation operator.
They keep the soft mode and then keep some sort of counter term, roughly speaking, to get rid of it. So the hope is that question is whether it's doing the second thing. That is effectively dropping that.
Actually, let me just think about what you said. So in the formulation where you keep the vacuum, keep these zero modes, the statement is that if I were to compute a generic S matrix with these zero modes turned on, step number one. Now that I have all these zero modes, you have an infinite dimensional Hilbert space. Let's say I work in a box. So you have some number of zero modes. So you have a degeneracy of vacua labeled by the value of theta, let's say, right? Now, the idea there in that formulation is that if I compute any generic S matrix in gauge theories, the vacuum will change. You can never have a well-defined S matrix in which the in vacuum is the same as the out vacuum. Okay, so there's a necessary change, vacuum transition that's occurring. That's the memory effect. Now, okay, so that's just a fact in this formulation where you keep the zero modes.
Good.
Now, if I drop the zero modes, then I don't have infinite vacuum degeneracy. I just have a unique vacuum, and then I just have a well-defined S matrix with it's not clear. So my question is, it's not clear that this S matrix where there's no vacuum transition, because now I don't even have a degeneracy of vacua, is equivalent to this old S matrix.
But for any process that is happening on scale small compared to the box, it can't tell the difference. So it should be the same, right? How can you? The box could be the size of our universe. We're doing LHC experiments. You can't tell the difference. Just at the level of formalism, though, it seems cleaner to me.
Right, because in the original formalism, the way this memory effect is coming in is precisely because you have some in state which is transitioning into a different out state. It's not, so I'm going beyond forward scattering.
Yeah.
And that because these charged particles produce long range electric fields, and those long range electric fields are therefore changing as a function of time, and that's the memory effect. That's the thing that gives you vacuum transition. But if I'm getting rid of these zero modes, I've gotten rid of these long range effects.
Only at that one particular.
Only at that one particular mode. But that's the mode that's relevant for this vacuum transition.
So memory is something, or something has gone past and you wait infinitely long. Then.
Yeah, you have to wait
So you
infinitely.
don't wait infinitely long, you wait for 1 year. That has not gone. Right, I mean, you cannot, right?
Okay, let me ask a downward question. Sorry, please don't mind. I mean, if two theories give the same cross sections, then one would say physically they are the same. And then if you have a choice where your S matrix is unitary,
Yeah.
maybe you choose that. So we're all happy that there's
Yeah,
an S
that's fair. Yeah, that's so totally.
That's fair enough, right?
Yeah.
And which of them, in Shiraz's and your box, which of the two theories gives a unitary S matrix? The one where you throw in the zero mode, or you keep it? That's the part I didn't understand.
It seems to be the one where you throw.
You throw it out.
Because all the troubles are coming from the zero. Or not.
Yeah. But is throwing away so trivial? Like it may be that the appropriate states, for example, actually this is another thing that I have been wondering about. In fact, it's something that Andy has suggested as a potential resolution of this information paradox, is that throwing away the soft modes actually is the thing that changes a pure state to a mixed state. So it might be that the appropriate S matrix to compute in the theory without the soft modes is some S matrix evaluated not in a pure state, but in a mixed state.
Well, I was just thinking from a Hilbert space point. Hilbert space point of view, if you can produce and you can impose these boundary conditions, there's no inconsistency. Then that gives you one definition of it. True. Now we can just compute in this definition.
Yeah. But the question is that definition equivalent to starting with the definition in which you include these modes and somehow throw them away?
Let's say it's not completely equivalent, but anyway, those modes are giving trouble. So once you include those modes, you want something, you want to then find a definition that removes the trouble. This is one such level. And it will be guaranteed to be.
No, but the reason we have to show that it's equivalent is because the formulation in which you keep the zero modes is definitely has the various correct features. It gives us the soft theorem, which we know is true. It gives us infrared divergences, which we know is true. The cancellation.
But this can only change things on the scale of the box. I'm sorry, everyone's leaving some animation and continuing to talk. Right? So anything that's happening in a lab that's small compared to the box cannot be different between them.
I'm sorry, which I don't understand about that is S matrix refers to asymptotic statements, right? So that, of course, can be different.
That can be different. But if you compute anything you can compute in a lab, that cannot be different. So we give the same predictions for LHC.
But I mean, anyway, the predictions of all cross sections, we all agree they are the same.
That's right, I suppose.
But
Okay,
maybe
no. But the point is that scattering experiments are not the only experiments you can do. If you do scattering plus memory,
but you do
that
memory,
has more information than just cross.
we cannot wait for infinite time. We can only wait for some finite time.
True.
So for any time we can reasonably wait for it, do the same prediction. Now please go on. We can talk about this.
Okay. So memory are additional experiments in which the two descriptions will differ. It's an experiment.
Well, I don't know what memory corresponds to in the other formula.
Okay, but that's the question. Then I'm sorry, I'm so trained as a particle physicist. Okay, so I take the system in a box, right? And I do these two different ways of quantizing, let's say. And now, in your way, where you're keeping these modes, there is a memory effect, which I have to understand.
There is a change in the vacuum.
It's change, but it's measurable through some
It's measurable. Yeah, there's an experiment.
If something happens and then a particle that was there, has it moved or has it got a kick?
For GR, I sort of understood it once. Here, there's something else.
Yeah, it's a velocity kick for an electron.
Yeah, just an integrated impulse.
Yeah,
For
electromagnetism,
It's a very simple thing. Okay, but this integrated impulse you want to do over infinite time. Instead, we do it over 1 year, 1 day. cannot change, I feel.
Because it's never going to be zero energy. It's going to be so 1 over 1 year is the kind of energy you're measuring.
What's the size of the universe? How can there be a difference?
So then, is the concrete question whether you have a memory effect in the description without the zero?
Yeah, I mean, by memory effect, if we mean first do something, then take, then take size of box.
Yeah.
This measure over a time much smaller than size of box, but much larger than other scales in the process. I think clearly is yes. Because it's just that you don't do the impulse integral over or the life of the universe, you do it over a year. Seems to me that they can. Okay, I'll shut up.
Let me add though that there are other zero modes which correspond, for example, to the subleading soft theorem. Those never go away. Even in the fuzzy coolest state, the 1 over omega kind of the one that's related to infrared divergences, that soft pole does go away. But there's still the subleading soft graviton theorem. There's these log soft graviton theorems in the amplitude. Those are all still present, even after you do whatever dressing you want to do.
Does it invalidate the S matrix? Does it make the S matrix infinite? These other things.
The S matrix, at low energies, they become, no, not infinite. No, they're totally finite.
Then they're features.
No, they're totally finite. But they are still new zero modes. So there's still a vacuum degeneracy. That's my point. They are related to.
How can there be zero modes? I put this box, I put the boundary condition that I've removed this mode. Now there are no zero.
Well, these zero modes don't. I'm just saying there are other zero modes. So yeah, you've removed these zero modes.
But if I've done it in this box, now there's no room for zero modes. Only possible zero modes are k equals 0 and I remove them.
No. So in this box analogy, you're looking at, let's say, what you're actually doing is you're looking at the radial electric field, so UR component or the TR component of the field strength, and you're removing the k equal to 0 mode for that. But there's other components which also have k equal to 0. Like in fact, for the subleading, let's take the photon example. For the subleading soft photon, there's let me remember what it was. FRA, A being again the angular component. So if I take FRA, they also have k equal to 0 modes. And
I have a box.
Yeah.
I have all my photon, all my solutions to the wave equation subject to the boundary condition. Then now with these boundary conditions, I thought there are no solutions to the wave equations with k equals 0. Therefore, we've removed everything.
This is in the case where we
threw away everything, set the theta equals 0. I just put that there. Now I just solve my equation. I do it like an undergrad. Right. There's a box, there's a boundary. I find all solutions.
Yeah.
I'll find no solution with k not equal to k equals 0. Therefore, we're done.
This is where the box is kind of the that's where I'm getting confused, because the other zero modes that I was talking about, they occur and that will only make sense in the continuum limit, where you take a derivative and then take omega to 0.
So maybe you're saying that there will be interesting features coming from not just one mode, but from the next guy.
From the next guy.
That's correct. That's what we want, right? But as long as the S matrix is well defined, it's unitary. Unless you're telling me I'm being stupid.
No, I'm not, and I don't know.
Okay, please go on.
Yeah. Okay.
And now that you have another mode, whenever there is a natural break, we will.
Okay, I'll just end by just telling you about solutions to Maxwell's equations, which everyone should know. So that'll be a good place to end. Hopefully, there won't be any questions for that part. Okay. So as I said, so this is my action, and what I'm going to do is simply evaluate it on shell again with some I epsilon prescription, which we'll get to it when we get to it. So the step number 1 is to just kind of list all the solutions, and I'm not going to classify all possible solutions. I'm just going to tell you literally the one feature that I will need for the talk. And so this is how I construct my solutions. So I'm going to start with the gauge field, and I'm using capital indices to denote d plus 2-dimensional Minkowski spacetime. And little a indices are going to be just d dimensions. Okay, so this is in d plus 2 dimensions. It depends on x. And I want to break it up into 2 pieces. So again, I'm going to do the usual thing. I'm going to solve it in Fourier space. That's the easiest thing to do. But I have to be very careful because the fact that the gauge field has a boundary term means that I can't do Fourier transforms. So I have to separate that piece out and then do the Fourier transform for everything else. So I'm going to separate it out. I'm going to say there's an A hat, which I'm going to define as A hat.
Sorry, I was sleeping. What is it? What is this separated out?
Yeah.
There is-
I'm writing it. 1 minute. So I'm solving Maxwell's equation now, literally just old school Maxwell's equations, and I'm going to do it in the usual way in Fourier space. Go to Fourier space. But before going to Fourier space, I need to ensure that the field I'm starting with admits a Fourier transform. So to do that, I'm going to first separate out the boundary value, which again, now here is where the assumption goes. I'm assuming that the boundary is pure gauge, which is only true if I have no magnetic charge. Otherwise you should add in principle something that looks like heavy, and this field couples to magnetic branes if I'm in higher dimensions to extended objects, but in 4 dimensions to magnetic field particles. So if I was literally in 4 dimensions, then this can be the 2-dimensional volume form, and then I just turn on a second field. So now I still have 2 polarizations. One of them couples to the electric charge, the other one couples to the magnetic charge. Okay, but here I'm going to assume just for this talk that there are no magnetic charges. So the boundary value of the gauge field is pure gauge. And this part of the field is the field that vanishes on the boundary. So it goes to 0 at infinity. Therefore, I can Fourier transform. So that's the part I'm going to Fourier transform. Okay, and to solve it, of course, I need to fix some small gauge, and I'm going to fix a very simple gauge condition, which is this axial gauge, where NA is just 1 minus 1. Okay, so now let's just go to momentum space. So I'm going to now I'm going to write out the solution for this A hat. I just move to momentum space, and I'm going to solve it again in the usual way. So I take my A hat A, which is in momentum space a function of L, and I'm going to write it in a basis, expand it out in a basis of vectors, basis of orthogonal vectors. And the orthogonal basis that I'm going to work with is LA, kind of trivially by convenience, I'm going to choose LA. Of one of my basis vectors, NA to be the other one. And then I'm going to introduce polarization vectors. Remember, all of this is off shell right now. There's no on shell. So some arbitrary basis of fields. And then just expand A in this basis. Okay, and let me just tell you the solution. So the full solution, when I do this for Maxwell's equations, is E times J over NA. So the LA component is 0 because of this gauge condition. So that sets the LA component to 0. The NA component turns out to be this. Again, I'm literally plugging in Maxwell's equation. It's a linear equation. Textbook stuff. And then this is the so this is the longitudinal polarization, roughly, that on shell goes away. When I take the on shell, this will not contribute in the on shell limit. But then you also have the transverse polarization. So the thing that's proportional to this epsilon A, the polarization tensor.
What is J? Which component?
It's NAJ. Okay, and let me write out. Let me write this out. So this is L, and this part is A hat AL. So these are the transfers.
So far, you've just imposed gauge.
Yeah, well, I know I've also solved equations.
You've solved it.
So this is Maxwell's equation. This is the solution, and I'm just going to write down the solution. Okay. Okay, and this solution is kind of that's the radiative part. So the radiative part sits in there, and those are where the longitudinal the transverse polarization show up. This is given by, I'm just 2 pi times O A times delta L squared. So this is the on-shell degrees of freedom here. And then of course there's a coupling to the term. Should be no trouble whatsoever. And again, now this is so I'm going to only mention the one crucial fact about this that I'm caring about is so to solve Maxwell's equations, I literally just need to take the Fourier transform of this. But of course, there's a 1 over L squared, so that's problematic. So we fix this by doing putting in an I epsilon prescription. That's the usual way of doing it. And depending on which I epsilon prescription I choose for this 1 over L squared, I pick up different radiative degrees of freedom over here. So in particular, if I replace my L squared with minus L0 minus plus I epsilon in this way, squared plus L vector squared. So if I do this deformation, then the corresponding O is precisely the in or the out creation operators. So with the plus or minus. So this OA gets a move to, this is again the standard prescription. So this is essentially, one of them is the retarded propagator, the other one is the advanced propagator. And depending on whether I use the retarded or the advanced propagator, this radiative mode sitting out here is either the in creation operators or the out creation operators. Okay, and then when I take this and again, I'm only going to keep the one important thing is that if I compute a difference between the in minus out, which is the thing that goes into the LSE theorem, that's the thing you use to compute the S matrix. So O A plus L minus O A minus L. So the thing to know, the reason I'm taking this minus sign is because this doesn't depend on what I epsilon prescription I use. The whole point is that you change an I epsilon here, this changes in a way such that this total sum is still the full gauge field, right? That's the whole point. So if I take a difference between O plus and O minus, that part will just drop out completely. And the difference is related just to the current. This is essentially the statement what LSE theorem is telling us, that the O plus insertions of O plus minus O minus is simply obtained by inserting the current instead. And then doing that path. This is a statement of, this is kind of it's a derivation, I think, of just the LSE theorem. So this is, again, on shell, because all of these O's are always multiplied by delta L squared. So these things, anyway, they only make sense if I'm on shell. Minus E times I, this is where the I will come in, J A of L, with the delta L squared is 0. This is the statement. This is essentially LSE theorem.
Sorry, Prahar. You were just solving some equations of motion subject to some boundary conditions.
Yeah.
That solution had a unique solution. Yes, sir.
Yes, it has a unique solution.
Okay. Now this plus minus is just some way of writing that.
Yeah. So it's a unique solution again up to the radiative part, right? Up to the free solution, which we don't know.
Yes.
So we have to pick a free solution. So we either pick the one that corresponds to an ingoing particle, right? So that's the thing that for which the gauge field vanishes at Scri plus, because it represents an ingoing, there has to be incoming flux, but no outgoing flux. Or you can choose the one that has outgoing flux, but not incoming flux. So that's the only freedom that we have. It's a unique solution up to the solution to the homogeneous solution. Okay, so here that's what I was calling O plus minus. O plus corresponds to an outgoing photon, free photon. O minus corresponds to an incoming free photon. And that's the freedom. And what Maxwell's equation is telling you, this is essentially just a rewriting of LSE, is that if I take an outgoing photon minus an incoming photon, that this difference between these homogeneous solutions, again, because the homogeneous solution is always on shell, it's always delta, that is always equal to the current in this way. Again, as long as L is on shell. This is not true off shell, but as long as there's a delta function multiplying this whole thing, you can replace it with the current. So that's what LSE is telling.
So if you had a current that was doing something, then you would have no radiation at the beginning, but you would have it.
You would have some radiation. That's literally just all that is.
Linear current.
Yeah. Okay, so I will just stop here. this is kind of all for these solutions, this is really all you need to know because this is very basic stuff. And then starting from in my next talk, what I'll do is I will take, now I've given you everything you need to know. This is my full solution. It contains an A hat piece, which I have written down the exact solution for you. And actually it turns out the only part that I will care about is this. And then it also has the theta piece, which I've kept track of. I'm going to plug in this whole solution into the action I wrote down and then process. And that process will require us to use some complicated equations from other previous papers, which I'll briefly outline how we derived it, but I won't have time to go into any detail because these are like long papers in themselves. And then the outcome of doing this entire procedure will be the solved effective. Yeah, I'll stop here.